Hello, everyone. So today we're going to be taking a little bit of a break to review all that we've so far learned about the thermodynamics of non-reactive systems. So essentially, what just happens if I'm compressing or expanding or just moving around a chemical system. So when I'm doing this, the good equation to start with is going to be our classic first law equation, where any change in energy of the system is going to be strictly due to energy entering or leaving through work or heat. Now, unfortunately, this just kind of kicks the can down the road as we now need equations for work and heat. So the easiest one is going to be for work, at which point this is classically referred to as PV work, where we're assuming that almost all of our work is coming from expansion or compression of the system, which is not atypical for an ideal gas. Now, one of the things I want to emphasize is that this is negative PDV, but the pressure we're talking about is going to be the external or applied pressure, not the actual internal pressure of the system, and that can be an important difference. However, we can also end up rephrasing our internal energy of the system as in terms of changes of volume and temperature, where the internal energy change is equal to the internal pressure times the change in volume plus the isochoric heat capacity times the change in temperature. And we have a similar expression for any changes in enthalpy, where enthalpy changes with pressure as negative Joule-Thomson coefficient times the isobaric heat capacity times the pressure plus the isobaric heat capacity times the change in temperature. So again, one of the things to note here is that we do see the isobaric heat capacity show up twice, once in a temperature dependence and once in a pressure dependence, as kind of a modulation of how pressure and temperature are essentially correlated through the Joule-Thomson coefficient. However, it's also nice to have a direct relationship in between enthalpy and internal energy. And again, our enthalpy will always be greater than our internal energy by a factor of PV. Now, most of the time, what we're actually going to be more concerned about is the infinitesimal change, or the changes in enthalpy, which can be expressed as the change in internal energy plus the change in PV, which is often separated out as PDV plus VDP. So again, these are a very nice set of general equations. So all of these equations make no assumption as to whether we're working with an ideal gas, a solid, a liquid, doesn't matter. And so these are a nice general set of equations. However, oftentimes we're going to be looking at gases, and specifically the nice simple form of the ideal gas, as this gives me a lot of more condensed equations to try and work with and play around with. Also, another wonderful thing about working with ideal gases is that what we find is that because there's no energy caught up in intermolecular bonds, we have several terms drop out. Specifically, the Joule-Thomson coefficient and the internal pressure are both going to be equal to 0, because these essentially are going to be indicators of intermolecular forces which just aren't present. Now, one of the things that you may note is that this is actually a fairly small subset of equations that we need to really end up doing anything we want in most of simple thermodynamics. However, we do run into a problem in that while these equations are simple, they may not always be useful, especially when we're dealing with things such as external pressure. Ooh, that's a bit of a can of worms. So in practice, what we often are looking at is the changes of one of our 4 fundamental thermodynamic properties: heat, work, internal energy, and enthalpy, under one of the 4 major limiting conditions that we've brought up this semester: isothermal, isobaric, isochoric, and adiabatic. So constant temperature, pressure, heat, and or sorry, constant temperature, pressure, volume, and heat. So let's go ahead and try and look at how some of these systems simplify under these conditions. So we're actually going to work essentially right from left with adiabatic conditions. So let's go ahead and start with our general equation. So the change in internal energy for an adiabatic system. Well, in this case, we're actually stuck with our relatively general equation. Because if I have an adiabatic system, we can have both a change in volume and a change in temperature of our system. So this equation doesn't actually really simplify that much. We see a very similar trend for our enthalpy, where what we get is our general equation for enthalpy with a change in pressure and temperature. However, we can simplify these equations for an ideal gas system, where my internal energy drops down to CV dt and my enthalpy drops down to Cp dt. And these are going to be some of our typical workhorse equations. However, when we're looking at heat and work, we get a little bit luckier because by definition, the heat of an adiabatic system is zero. And because that's zero, it actually gives us an extra simple equation to work with for our work, because our internal energy has to be equal to our work plus heat, which means that our work is equal to our internal energy, which also means that by measuring the temperature of an adiabatic system, you can also directly measure the work of an adiabatic system, as long as you essentially know the identity of your gas and its heat capacity. However, again, this expression gets a little bit trickier for non-ideal systems. However, if we go to an isochoric system, we actually get a little bit lucky as some extra terms start dropping out. So for example, with our internal energy, we have no CV term, or a change in volume term. So our internal energy is entirely due to any sort of changes in temperature. However, our enthalpy expression stays relatively fixed, whether it's under non-ideal or ideal scenarios. However, because work is equal to negative PdV and our dV is zero, we also get a very simple expression for work. Gotta love it when that happens. And because our work is equal to zero, this means we actually get kind of lucky with heat. So our heat is just going to be equal to our change in internal energy. So again, by measuring the change in temperature and knowing the identity of the species, we get straight at the heat of an isochoric, of any isochoric behavior. Then that brings us to an isobaric scenario. So under isobaric conditions, well, it turns out our internal energy doesn't simplify that much. So internal energy is not the best thing to use under isobaric conditions. However, enthalpy was designed for this, as we no longer have to worry about any Joule-Thomson effects, and we simply are relying on the temperature. Now, we do get an extra little freebie under isobaric conditions, and that's that our external pressure now has a single concrete value and no volume dependence. So we also love this, as it makes this integral rather straightforward, as it really is just negative P delta V. So again, wonderful work behavior under isobaric conditions. And we get a little bit of freebie for heat because under these conditions, our heat is entirely enthalpic in nature. So our heat is equal to our change in enthalpy. So again, by measuring our temperature and knowing the identity of our substance, we get straight at the heat of our system. So again, under limiting conditions, heat's actually fairly nice for all three of these sets, and work as well. However, things get a little bit trickier once we go to isothermal. Because under isothermal conditions, well, you notice this dT that tends to dominate? Well, it's not there for our internal energy and enthalpy. So for example, looking at our enthalpy expression, what we find is that with dt dropping out, all we have is essentially our intermolecular forces base term with its pressure dependence. But that also means for an ideal gas, our change in enthalpy for an isothermal case is going to be zero. And we see something very similar for internal energy, where our internal energy is going to be based entirely on the internal pressure of a system, which for an ideal gas doesn't exist. Now, this also brings us to an interesting case for work. So in work, what we end up having is unfortunately our general expression of our negative external pressure times the change in volume. However, if we have reversible conditions, as well as an ideal gas, we're actually kind of lucky and we can do some math magic and some clever integration to get it down to nRT times the natural log of a change of volumes for, say, a compression, for an isothermal reversible compression. However, this is a fair number of limitations, so we don't always get there, but you can also still imagine this as the minimum amount of work required for a compression, or the maximum you can get out of an expansion. However, once we're down to our heat, now we get a little bit trickier, because our heat is going to be equal to our internal energy minus our work term. So unfortunately, this gets a little bit messy. However, if we're under an ideal gas, it actually simplifies down to just the negative of our work, or px dv. And if we're very lucky and we have that same reversible conditions, our heat is just going to be nRT over natural log of the ratio of volumes, because any energy that entered as work has to leave as heat, otherwise the temp builds up. So this brings us to the end of our kind of quick review of the equations we have so far. However, you may notice that none of these involve chemical reactions. So we're going to start talking about those next time. Till then, take care.